So what you're going to want out for today are the Chapter 9 notes. More specifically, if you want to flip to, let's see, what page is this? 10. If you want to flip to page 10, so if you flip to page 10, this is where you may recognize these. Some people got them last year, others did not. So you guys don't have to worry about writing anything in. Everything is already written in for you. But what I like to do is I like to review shapes as a class, especially because when I had asked everybody about, if you remember shapes, Lewis structures, and people said, yeah, Lewis structures, but shapes are kind of iffy. So before we get into shapes, just to review some things from the video, some questions. When it comes to if an entire molecule is polar. So when we look at molecular polarity, we have been looking at if a bond is polar, just one bond. When we look at an entire molecule, if we have a symmetric molecule, it's always nonpolar. We're going to talk about fundamental shapes. All of the fundamental shapes are nonpolar as long as all of the atoms around the central are the same. And then if we have lone pairs, that almost always means the molecule will be polar. There are a couple of exceptions. So if it's linear or square planar, those lone pairs actually cancel out. So this actually came right out of your notes. We'll talk about fundamental versus derived shapes today, and how that plays into electron domain geometry versus molecular geometry. So first, we're going to talk about electron. This got a lot bigger than it was supposed to be. Okay. So for electron domains, when we talk about electron domain geometry, we are talking about what is the shape of the electron clouds around the central atom. So when we talk about electron domain geometry, all we're doing is counting the regions of electrons around the central atom. So for example, if I have this little model, right, my central atom is in the middle, and I have 4 areas of electrons around the central atom. When we count areas of electrons, non-bonding pairs, those are lone pairs. So a lone pair counts as 1 area of electrons. Any bonds count as 1 area of electrons. If it's a single bond, that's 1 area of electrons. A double bond, it's still 1 area that the electrons are in. If it's a triple bond, it's still 1 area of electrons. And then what we do is we look at what that shape of all of the electron areas creates. When it comes to the electron domain geometry, it is always one of what I call the fundamental shapes. So the fundamental shapes are linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. So if a question says, what is the electron domain geometry? It is always one of these fundamental shapes. Because the area of electrons, you'll always have 2 areas of electrons, or 3 areas of electrons. No matter what the area is, it's still just an area. So an electron domain geometry is one of these fundamental shapes. Then we get into molecular geometry. So the molecular geometries take into account how the lone pairs actually affect the bonded atoms. And so this actually was in your notes as well, but here's where I had someone blow up all of these balloons. So what we're going to do is we're going to look at each of the fundamental shapes and how making changes to the fundamental shape affects the geometry. So with all of these balloon shapes, imagine that the very middle where I'm holding is the central atom. And then each balloon is a bonded atom. So if I have a central atom and there are 2 atoms bonded, so you have 2 atoms bonded, 0 lone pairs, that results in the linear molecular geometry. Right? This is linear. Linear results in a 180-degree bond angle. So there was a question, do we have to know the shapes? Yes. Do we have to know the bond angles? Yes, of the fundamental shapes. So you need to know the bond angles of linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And then we'll talk about how the bond angles change based on when we make changes to the fundamental shapes. So then you have the examples in your notes, but CO2. So notice this is one area of electrons, one area of electrons. So this is linear. It's a 180-degree bond angle. Nothing really else to do with these things. Then we get to, right, here's my central atom in the middle, and I have 3 atoms bonded. This would be an example of like BH3 or BF3, because boron is an exception. So when you have 3 atoms bonded to the central, 0 lone pairs, it's the same as the fundamental shape, it's trigonal planar. Now, hopefully everybody at home is paying attention and they're going to get a nice surprise. Okay. So, now I turned an atom into a lone pair. So every time I pop a balloon, it becomes a lone pair. So now instead of having a molecular geometry of trigonal planar, we've changed it because lone pairs are going to push the bonded atoms together. Lone pairs want to repel everything around it. So it's still trigonal planar in terms of electron domain geometry. There's still 1, 2, 3 areas of electrons. But the molecular geometry is now different. Now, whether you call this bent or angular, it doesn't matter. More and more often now we're seeing 2 atoms bonded and 1 lone pair also being called bent. So either term is fine. But now the bond angles are no longer 120 degrees because this lone pair is pushing these 2 atoms together. So the bond angle is now something less than 120. You don't have to know exactly what it is, you just know it's less than 120 now because the lone pairs are repelling the bonds and they're pushing the atoms together. So, fundamental shape, and then we can derive it into 2 different shapes. All right, so then we get to, let's see, where's my tetrahedral? 2, 1, 2, 3, there it is. All right, so now we get to tetrahedral. Now, tetrahedral is where people start to get tripped up with bond angles, because when you draw it on a piece of paper, right, we don't use the solid and the dashed line to represent 3-dimensional structures. Typically, you draw it with C and then H, 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 and H, which is fine. But in reality, the bond angles are not 90 degrees. They're actually 109.5 degrees. So the central atom is here in the middle. I have 4 atoms bonded. This is actually what tetrahedral atoms look like. Here's another example with my little model. This is what CH4 actually looks like. So the bond angles are not 90 degrees. They're 109.5. So the electron domain geometry and the molecular geometry right now are the same. So now, I don't like doing this. Okay, here we go. So now, we have a lone pair. Right, the lone pair is pushing these 3 atoms down. So now we have 3 atoms bonded to the central with 1 lone pair. This results in a trigonal pyramidal molecular geometry. So the molecule itself has a trigonal pyramidal geometry. Notice how the electron domain geometry is the same no matter what, because there's always 4 areas of electrons around the central atom. But trigonal pyramidal, right, now the bond angle is going to be somewhere less than 109.5. It's different based on the atom. It's going to be somewhere less than 109.5. All right. Okay. So now we have 2 lone pairs. So central atom is still here, but now we have two lone pairs, two atoms bonded to the central. So now it's going to push these atoms together even further. Now it's really less than 109.5. This is an example of water. Two atoms bonded, two lone pairs, results in the molecular geometry of bent. So again, this is bent. The 2-1 could be angular, but this is always bent. Water is bent. But again, the electron domain geometry is always going to be tetrahedral. There's always 4 areas of electrons around the central. The molecular geometry is where it starts to change. Right? So now we're going to get into 1, 2, is this my 5? 1, 2, 3, 4, 5, yes. Okay. So now we're going to get into the expanded valence. Expanded valence just means that there's more than 8 electrons around the central. So, when we have 5 atoms bonded to the central, so a central atom is here in the middle, there's 1, 2, 3, 4, 5. This is trigonal bipyramidal. So 5 atoms bonded, 0 lone pairs, trigonal bipyramidal. Now these bond angles get a little bit different. We have 2 positions in trigonal bipyramidal. We have what's called the axial, we have the equatorial. So think about like the equator is around the Earth. So the equatorial atoms are around, axial, like an axis, is the top and the bottom. So the bond angle between the equatorial is actually, if we look at it, so it actually is trigonal planar. So the equatorial is 120 degrees. Between the axial and equatorial is 90 degrees. And between the axial and axial is 180. So there's actually 3 bond angles with the trigonal bipyramidal. Now, if we pop a balloon, we want to add a lone pair. Because we have the different bond angles here, we want to add the lone pair where it's going to be furthest away from the other atoms. And that's where the bond angle is the greatest. So we're going to add it to the equatorial position first. Oh man, I lost an angle. Okay, here we go. So, let's try to hold them all together. Now we have a lone pair. Alright, so we have a lone pair that's in the equatorial position. It's right here. So now I have 4 atoms bonded to the central, 1 lone pair. This results in the seesaw molecular geometry, because if you think about it, if you turn it on its side, right, it's like a seesaw. So 4 atoms bonded, 1 lone pair results in seesaw. Bond angles are still going to be essentially the same, 90, 120, 180. Then we add another lone pair, so I'm going to add it to the equatorial. Maybe. Oh, I'm left-handed. It's like the splash. All right, so I add another one to the equatorial. Hang on, let me get this instead. Here we go. Okay. There we go. All right, so now I add another lone pair to the equatorial. So I have 3 atoms bonded, 2 lone pairs. That's T-shaped. So notice here we have T-shaped. Again, the electrons, the lone pairs, are as far apart as possible. And then finally, I remove the 3rd lone pair, again from equatorial, so that they're as far apart as possible. And now I have a straight line. So seesaw and T-shaped are both polar because of the lone pairs. In linear, even though we have lone pairs, all 3 of the lone pairs are pulling evenly, and they cancel each other out. So this is the example of the linear that has lone pairs that's actually nonpolar. So trigonal bipyramidal is nonpolar, and linear is nonpolar. The rest of them will be polar. And we'll look at some examples of polarity as well. So then we get to octahedral. So I'll show you what the octahedral looks like with the balloons, but I have a feeling they're all going to fall apart again. So here's what octahedral actually looks like in terms of 3-dimensional space. You have an atom on top and bottom, and then you have 4 around. All of these bond angles are 90. And then if you want to go from the top to the bottom, it's 180. So in this case, we have bond angles of 90 and 180. So 6 atoms bonded, 0 lone pairs gives us octahedral. So notice electron domain and molecular are the same. Then we start adding lone pairs. Now in this case, it doesn't actually matter where we pick to add the lone pairs because they're all 90 degrees apart. I'm going to show you with this one because I'm sure these are going to fall apart. So here's my octahedral. If I remove, there we go. All right, so now I have a lone pair down here. This creates a square pyramid because notice this makes a square, and if I connect all the sides, it makes a pyramid. So 5 atoms bonded, 1 lone pair, square pyramid, all right, or square pyramidal. This is polar because there's just 1 lone pair of electrons. Well, then when it comes time to remove another atom, add another lone pair, you want to add it as far apart as possible from this lone pair. So I'm going to make sure that I put the lone pair on the top. Now this is what we call square planar. Makes a square, and it's even in the plane. Now square planar, because you have 1 lone pair on top and 1 lone pair on bottom, those lone pairs will actually cancel out. So square planar is the other one, the other molecular geometry that has lone pairs that's actually nonpolar. And then we can continue to remove. Okay. Well, we can continue to remove, so we can remove another, put a lone pair here. That creates T-shaped. And then put another lone pair, creates linear. All right, and you have those 2 in your notes as well. The very last page of your notes, so essentially all of this that we went through, right, is on pages 10, 11, 12, and then 13 has a page that looks like this. Now we haven't talked about hybridization yet, that's Monday. So when you look at hybridization, don't worry about that yet. But page 13 of the notes actually shows you how many bonded pairs. So essentially you can do how many atoms are bonded to the central, how many lone pairs are there, what the geometry is, so that's molecular geometry, and whether it's polar or nonpolar. Right, so we have a few kind of pages at the end that are going to be helpful as we look at geometry. So what we're going to do is we're going to actually go through some examples together before you guys work with your groups, just so you have extra practice to look at. So this is on page 5. This is on page 5 of the notes. I need to move all of these before I step on it. On page 5, it says draw the Lewis structure. Determine the electron domain and the molecular geometry. So it's more practice with drawing Lewis structures. You have to be able to draw the Lewis structure to be able to figure out the shape. So, for number 1, again, we go through the exact same process that we have been with Lewis structures. So we count the valence electrons. So boron has 3. And each hydrogen has 1. So we will have 6 valence electrons. So boron's going to be in the middle. We'll put 3 hydrogens around it. Does B and H have the potential to multiple bond? No. Neither one is part of cons. So all single bonds. I needed to place 6 electrons, 2, 4. There's 6 electrons. So there's the Lewis structure. So then we need the electron domain geometry and the molecular geometry. And we're also going to look at if it's polar or not, just to help with polarity. So electron domain. We focus on the central atom. All of the geometries, whether it's electron domain or molecular, is focusing on the central atom. So there is 1, 2, 3 areas of electrons. 3 areas of electrons around the central atom. What's the fundamental shape with 3 areas of electrons? Trigonal planar. Electron domain geometry is always one of those fundamental shapes. So in the molecular geometry, we look at how many atoms are bonded and how many lone pairs do we have. So in this case, we have 1, 2, 3 atoms bonded, 0 lone pairs on the central atom. So 3 atoms bonded and 0 lone pairs results in what molecular geometry? Trigonal planar, right? They could be the same thing. The fundamental shapes are the ones 2, 0, 3, 0, 4, 0, 5, 0, 6, 0. All right, so no lone pairs. That's what that means. Then we'll finally look at if it's polar or not. So when it comes to polarity, first you have to have polar bonds. None of these bonds are polar because boron and hydrogen are both not very electronegative. But when you have a fundamental shape, if you have a fundamental shape and all of the atoms, all of the terminal atoms are the same, it's nonpolar. I'm just going to put NP for nonpolar. So what I want to have you guys do is only focus on the Lewis structures. But for 2, 3, and 4, just draw the Lewis structures. Don't worry about the shapes. We'll go through the shapes and the polarity together. But draw the Lewis structures for 2, 3, and 4. The valence. This is too much math. 42, 46, 48. All right, so we have Si in the middle. We have 6 fluorines. Here's going to be the biggest thing when you're drawing Lewis structures, especially on tests when you are, pressed for time. Don't forget lone pairs. I know it's a lot of dots to draw, but just don't forget your lone pairs. So there's SiF6, however, it's 2 minus. So don't forget to put it in brackets with the charge on the outside. So then we're looking at electron domain geometry, molecular geometry, and then if it's polar or not. So for the electron domain geometry, we're just looking at areas of electrons. 1, 2, 3, 4, 5, 6 areas of electrons around the central atom. Octahedral. So molecular geometry, we have 6 atoms bonded to the central, 0 lone pairs, which is what molecular geometry. Also octahedral. And so, because there are no lone pairs, that's the same as the fundamental shape. Since this is a fundamental shape and all of the central atom, or all of the surrounding atoms, are the same, this is a nonpolar molecule. The reason that this is nonpolar is because even though the SiF bonds are polar, so each one of these individual bonds are polar, which means we think about electronegativity, F is the most electronegative. So we have pulling up and pulling down, those cancel. Right? Pulling out and pulling out, those cancel. So even though the bonds are all polar, each of the dipoles cancel. You have one up, one down, one left, one right. So this has polar bonds, but is overall a non-polar molecule. So then we have PF5. So what's that? 540. So we have 1, 2, 3, 4, 5. So just surround. This does not have the potential to multiple bond. F is not part of cons. Again, lone pairs. not an ion, so you don't need it in brackets. So for electron domain geometry, you have 1, 2, 3, 4, 5 areas of electrons around the central. 5 areas of electrons is what fundamental shape? So trigonal bipyramidal. Trigonal bipyramidal is the fundamental shape with 5 atoms. That's different than trigonal pyramidal. So then for the molecular geometry, we have 1, 2, 3, 4, 5 atoms bonded to the central with 0 lone pairs on the central, which is what molecular geometry? Trigonal bipyramidal. And then again, since we're dealing with the fundamental shape, they're all the same. It's a nonpolar molecule. So 1, 2, and 3, we were looking at the fundamental shapes. Let's look at number 4. So for SF4, 28 and 6, 34. So S goes in the middle. Surround it with the fluorines. And if you don't draw the Lewis structure the same as what the shape should be, that's okay. For the Lewis structure, I'm going to make sure that in this case you would have single bonds to each fluorine. You have your lone pairs on your fluorines. The reason that it's only single bonds is because fluorine can't multiple bond, so it's not part of cons. Now count your valence. Always count your valence. Any extra will go on the central atom, especially when you get into the atoms that are in n equals 3 and below. So there's 8, so 32. I still need 2 more. It's going to go on the central atom. So here's where we'll look at electron domain and molecular, and in this case they're not going to be the same. So the electron domain geometry, I have 1, 2, 3, 4, 5 areas of electrons around the central atom. It doesn't matter whether they're bonds or lone pairs, but there are 5 areas of electrons. What electron domain geometry is 5 areas of electrons? Trigonal bipyramidal. The electron domain geometry is always one of the fundamental shapes. Now, molecular geometry, these are the ones that usually you have to go back in, maybe make flashcards, a Quizlet, something to remember all of your shapes. Because we now have 1, 2, 3, 4 atoms bonded to the central with 1 lone pair. So if you have 4 atoms bonded to the central with 1 lone pair, if you flip back in your notes, what molecular geometry is that? Page 11 is where we have the expanded valence with trigonal bipyramidal. 4 atoms bonded, 1 lone pair, results in seesaw. The trigonal bipyramidal and octahedral fundamental shapes are usually the geometries, like the molecular geometries that people have to memorize. So then really quick, because we have a lone pair, there's just 1 lone pair, there's nothing to cancel it out. This results in a polar molecule. We're getting into some molecules that will not have the fundamental shape for the molecular geometry, kind of like in 4. So if we take a look at 5 and 6. So go ahead and try to draw the Lewis structures. So just the Lewis structures for 5 and 6. So XeF4 and NO2 minus. So just draw the Lewis structures. And I know that it's weird because we have a noble gas as a central atom, but when we get into some of these bigger valences, these expanded valences, we will see noble gases as central atoms, even though that is weird. So when you draw XeF4, hopefully it looks like this. You have the 4 fluorine atoms bonded to Xe. Then you also have 2 lone pairs. Xe is so far down. I mean, it's in row 5 of the periodic table. It can definitely have an expanded valence. So then what we'll do is we will look at the electron domain geometry and the molecular geometry. So electron domain is always one of the fundamental shapes. There's 1, 2, 3, 4, 5, 6 areas of electrons around the central atom, which is what electron domain geometry? Octahedral. Octahedral is the largest electron domain geometry that we see. Then molecular geometry, we look at how many atoms are bonded and how many lone pairs. 1, 2, 3, 4 atoms bonded. 1, 2 lone pairs. Remember, you want the lone pairs as far apart as possible. So what molecular geometry has 4 atoms bonded, 2 lone pairs? Square. Now, whether you say square planar or square plane, either one works. And then remember that even though there are lone pairs, there are 2 exceptions to polarity of molecules with the lone pairs, and that is square planar and linear. Because the reason that this is not polar, so even though that these XEF bonds are polar, if I draw the dipole arrows, they all cancel. And then the lone pairs, there's one on top and there's one on the bottom. Those cancel. So when all of your dipole moments and your lone pairs cancel, it results in a nonpolar molecule. And then NO2 minus, so we have 5, 6 plus 1, 18 valence electrons. So NO2, I draw the structure. Does this have the potential to multiple bond? Yes. So if I do 6n plus 2, n is the number of atoms that is not hydrogen, so it's 3. Oh, man. 6n plus 2 is 20. So that means we can have 1 double bond. But I don't know where to put it. I could put it here. I could put it here. That means we have a resonance structure. Double bond could be on either side. So I'll go through, fill in the octets. 2, 4, 6, 8, 2, 4, 6, 8. And then we'll do the same thing. Now because they're both ions, I'm going to put them in brackets. Charge. So then we will look at electron domain geometry, molecular geometry, and the polarity. So electron domain geometry. Here's where we have to be careful. Here is one area of electrons. Here is one area of electrons. This is all just one area of electrons. So there's 1, 2, 3 areas of electrons around the central atom. So 3 areas of electrons around the central atom is what fundamental shape? Trigonal planar. Now the molecular geometry takes into account the lone pairs. So we have 2 atoms bonded to the central. It doesn't matter how it's bonded. It just matters that we have 2 atoms bonded to the central atom with 1 lone pair. Here's where you could use either term. You could say it's angular, or you could say it's bent. It's the same thing. 2 atoms bonded, 1 lone pair results in either angular or bent. Now, because there is this lone pair on the central atom, there's just 1 lone pair, that's going to result in a polar molecule. Okay, so that's kind of tying together Lewis structures and electron domain molecular geometries. So the last thing is actually looking at bond angles. So the biggest thing with these bond angles is not even necessarily angles themselves, but looking at how we can draw some of these structures. Because maybe we look at it and we're like, not sure. Remember that bond angles are based on the shape. So you still have to have the Lewis structure to figure out the bond angle. So let's draw the Lewis structures for these first, and then we'll figure out the bond angles. So Cl2CO. Typically, the way that it's written tells you what the structure looks like. So we have 2 Cl's, 1 C, and 1 O. Remember that the least electronegative atom is still going to be in the middle, which is C. So Cl2 and C. That means that 2 Cl's are going to be bonded to C. So there's 1 Cl, another Cl, bonded to carbon, and the carbon is bonded to oxygen. Now I drew single bonds between Cl and C right away because they can't multiple bond. But does C and O have the potential to multiple bond? Yes. I can count valence electrons. Oh man. Okay, let's do valence really quick. 2 times 7 is 4 plus 6. 24 valence electrons. Since there's the potential to multiple bond, we're going to do 6n plus 2. N is the total number of atoms that is not hydrogen. So 1, 2, 3, 4. So 6n plus 2 is 26. So it's a difference of just 2, which means 1 double bond. Now that tells me exactly what I need right here. Now we want to make sure that all of the octets are filled. So right now, both of the chlorines only have 2 electrons. And right now, oxygen only has 4. So there is Cl2CO. Now the bond angle, so it wants the ClC-Cl bond. Use a different color. It wants this bond angle. Well, it's based on the shape. What is the molecular geometry of this? We have 3 atoms bonded, 0 lone pairs on carbon. Trigonal planar. If it's trigonal planar, what are the bond angles in a trigonal planar molecule? 120. Because think about it, it's a circle. You're splitting the bonds. There's 3 bonds, so 360 divided by 3 is 120. And then it wants both of the bond angles in acetonitrile, which is CH3CN. So again, I'm going to show you how these are more organic types of molecules. So CH3 means that there are 3 H's bonded to the first C. So H, 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 and then we have another C and an N. So let's count valence electrons first. 4 plus 3 plus 4 plus 5, 7, 11, 16. Now, H can only single bond. Is there the potential of multiple bonding in this molecule, though? Yeah. So let's do 6n plus 2. N is the number of atoms, not hydrogen. So I don't count hydrogen in here. 1, 2, 3. So 18 plus 2 is 20. So there's a difference of 4, which means 2 double or 1 triple. Now here's where we have to kind of think a little bit. Right now, carbon already has 3 bonds. Carbon can only make how many bonds? 4. If I put a double bond here, that's going to give carbon more than 8 electrons. Carbon can't have more than 8. It's in row 2. So that means that this only can be a single bond. Carbon can only ever form 4 bonds, which means, what's my only other option to go between the C and the N? Triple. So I have 2, 4, 6, 8, 2, 4, 6, 8. Nitrogen only has 6. So there's acetonitrile. Now it wants 2 bond angles here. It wants one of these bond angles, and it wants this bond angle. So we actually have 2 different molecular geometries here. We have the molecular geometry around the first carbon and the molecular geometry around the second. So I'm going to number these C1 and C2. What is the molecular geometry around carbon 1? If there are 1, 2, 3, 4 atoms bonded to the central and 0 lone pairs. What's 4 atoms bonded, 0 lone pairs? Tetrahedral. So the molecular geometry of this part of the molecule is tetrahedral. What are the bond angles of a tetrahedral molecule? 109.5. Now we'll look at the second. So the molecular geometry of carbon 2. So I just numbered this one carbon 2. The second carbon has 2 atoms bonded to it. Has no lone pairs on it. 2 atoms bonded with 0 lone pairs is what shape? What molecular geometry? Linear. This is linear. If it's linear, what's the bond angle? 180. So molecules can have different bond angles within the molecule. You're just looking around a certain central atom. So actually, see if you guys can go through CS2 and AsCl5. So you're going to give the bond angle for SCS and then one of the chlorine, arsenic, chlorine bonds. So always start with drawing the Lewis structures. Always think about if you can form multiple bonds, or if you have an expanded valence. And then the angles are based on the molecular geometry. So once you have your structures, I went through for both of them. Structures, look at your molecular geometry, what that means about your bond angle. So CS2 is similar to CO2. The reason that we do 2 double bonds instead of a triple and a single is because of formal charge. That's why we say the more symmetric, the better. That's due to fewer formal charges. So since CS2 is linear, there's 2 atoms bonded, 0 lone pairs on the central, that bond angle is 180 degrees. AsCl5 I put on here because when you have a trigonal bipyramidal molecular geometry, you have multiple bond angles. So you can have a 90-degree bond angle. You can have 120 degrees. So from this chlorine to this chlorine, coming around, that's 120 degrees. Or from the axial to the bottom axial position is 180 degrees. So trigonal bipyramidal has 3 different bond angles. So questions on the Lewis structures, the geometries, bond angles. So you need to know bond angles for the fundamental shapes. Because anytime you add a lone pair, that just makes the bond angle less than whatever the fundamental shape bond angle was. Because water has a different bond angle than another bent molecule. Because it's based on the atoms as well. So you just need to know the angles for the fundamental, but you do need to know all of the different shapes. So for electron domain and molecular.